So occasionally I look for the examiner's reports on various exams just to read about what it was that kids found particularly difficult about that paper that I was, that I'm making for and about to record for. And this is the only message that came with this exam. So that's, I think, when you know when your um, YouTube content has got to the point where it's a little bit too niche.
This is the Further Mechanics 2 paper from 2021. Let's just go straight into it. We've got a centre of mass question first. It's one of the really nice, easy ones where it's just a rectangle here, so the centre of mass of this shape is quite obvious. It's just a half A across and 2A up, so we'll just put that down straight away. And then this centre of mass, well, the formula sheet says this, so we've got a sector here. So the centre of mass is here from the centre. It's obviously in the middle, and this is just the distance away from this centre here. Now the circle, this sector has kind of an angle here of pi over of just pi, right? Which makes alpha pi over 2 to make 2 alpha pi. So we'll say alpha is pi over 2, r is just a, right? Because the diameter is 2a, so the radius of the circle is just a. So we'll plug that information into there, we'll get this, which sorts out to be this. And so that's the distance across from here. And so the centre of this object, the centre of mass of this semicircle, is a plus 4a over 3 pi across, and then just 3a up, because it's 2a plus a to get 3a up, and we'll have that. And now, of course, we just need to work out the areas of these two shapes. So just a times 4a is just 4a squared, and then this is a half times pi r squared, where r is a, so it's just pi a squared over 2. And now the centre of mass, you could do this both at the same time if you want to, but I said horizontally away from OE or EO is just going to be, well, it's x bar times the total mass, or you can think of it as the total area, which are these two things added together. That's going to be equal to the area of this one times the distance away from OE this one is, so half A. So that's this distance here times by the area of this shape, plus the distance here times by the area of this shape, which we worked out, and then of course divided by the total area, which you usually write as times over here, but I just divided immediately. So it's kind of like a weighted average kind of thing. It's the same formula you use for x bar. We'll do actually a couple of times in this paper. But anyway, you sort this all out, and you eventually factorize out some a's, and I think I times everything by 6 here to get rid of all the fractions, and you eventually end up with this. And from OA, you just do basically exactly the same thing. You just look at the y bits instead, so this is going to be 2a times the area plus 3a times the area of this, and then just divide by the total area. Ends up being a tiny bit more simple, but you just sort it out and you get this. So those would be our two things that we have there. And now P is suspended freely, so it's suspended freely from O, and now the line here, the vertical line, is going to go through the centre of mass, which we worked out to be this. And now you can turn your page if you've got doing this exam for real, or of course if you're doing it in PowerPoint, you just copy the picture and rotate it around a bit. So now this vertical line goes through the centre of mass, which means this distance here, we actually worked out was, well, it's this distance here, which is this distance, and likewise this distance here, from O to this point is just this distance here, and the angle alpha, that's the angle from the downward vertical to OE. So that's going to be the angle alpha there. And now, of course, we have tan alpha is this over that, opposite over adjacent. Of course, you could factorize out some a's and some 3's, I think, from this line here. That cancels with that, that cancels with that. We just get a over 3 over a, which I think is just 1 over 3, and that would be our answer. Excellent. So that's question 1 done. Question number 2 then. We have this thing about it's the FA equals MA chapter where you have to sort of play around with A a bit to get it done. So let's just draw the picture, I guess, first. We've got MG obviously downwards, falling vertically. So MG going downwards, we've got resistance KV squared. So the resistance goes up the faster the thing is going, which is almost how resistance works. That's good. We'll have this, and then of course F equals MA says this minus this equals MA. But you can just write A as dV by dt, right? You learn in, what, regular A-level mechanics that the derivative of velocity with respect to time is the acceleration, so we can write this. And now we can separate this out and do a, it's a first order differential equation, is it? If you separate the t and the v, you can integrate later. First, I'm going to try and get this v squared object they're talking about. So k over mg is 1 over v squared, so that will put a v squared in there. The m's can now cancel. I factorised that mg just to try and make that big V squared. Now we can separate these variables to get this. And now, integrating this, I mean, we look in the formula booklet and we look for the thing that creates a log, and it's going to be this one here. First, I did something else to this apparently. Oh, I times both side, top and bottom of this fraction by v squared, big V squared, because that makes it, of course, this 1 over g can get brought out, and so can the v squared, and this just makes this the integral of 1 over big V squared minus little v squared, which looks exactly like this because I'm integrating with respect to little v, and big V is just a constant. So that's going to be exactly as necessary, I think, here, with a plus c at the end. Of course, what have I done here? Oh, I've just taken the 2v out there. Of course, plus c, well, you know that when t is 0, it's at rest. So when t is 0, v is 0. You plug those numbers in, log of v over v is log of 1, which is also 0, so therefore c is 0. I'm just checking that I definitely, yeah, that's correct. Good, so c goes away and we end up with the exact thing we had with v squared being this, because that's what I used there. Good, given interpretation of big V, there's a few ways of doing this. You could multiply across here and say k big V squared equals mg, which is kind of this situation, k big V squared equals mg, meaning that the two forces will be balanced when when little v becomes big V. And of course the two forces balance there's no acceleration, which means it's going at a constant velocity, so it's the terminal velocity. You could also think about the fact that if you try and make little v bigger than big V in this equation for the time, you end up doing log of a negative, which you can't do. So that would be a contradiction, and therefore big V is the largest that the velocity could ever be, otherwise known as terminal velocity. So a few justifications you could give there. At time t, p is forward distance of s, show s as this thing. So if you're showing displacement, you need to bust out this formula, f equals ma, but a is written as v dv by dx. So this is a standard formula that you should know. That's very helpful if you're looking for displacement or distance fallen, in this case. Well, okay, f is still what we had before, mg minus kv squared. X is s, they've just given us is distance s, so we'll just replace that. And this is actually an easier differential equation to sort out, because when you divide by this, this here is the form of the derivative of this, right? The derivative of this is minus 2kv, which isn't this, but it's the right form. And so this actually just integrates straight to a log, right? So if I integrate both sides, which I think I forgot to type, I did. If I integrate both sides here, the integral of ds is just s. The integral of this is log of this, with just some adjustment to make it actually work. So like I said, this differentiates to minus 2kv. I need an mv, so just times by m over 2k with a minus in front, and everything will cancel, and we'll end up with this, a plus c, of course, because, yeah. So that's good. That's not what they have here. So now we just have to spend the rest of our time trying to get the thing that they have. And I made a complete mess of this, and I couldn't be bothered to retype it up. But what I said was, okay, just times this by g over g, and also factorize out an mg over k from this to get this. So that seems really weird, but I'm just trying to force big V's in here, because like I can see mg over k here, so that's a big V over 2g at the front here, which is actually what I wanted. Sorry, it's big V squared, isn't it? Because V squared is this. Here's another V squared, so that's good. So I'll put those both in. And actually here as well, k times k over mg, so that's k over mg, which is 1 over v squared, just with a spare k there. So that's what I did first, and then I thought, okay, what else could I do here? Well, I can sort of, I think I multiplied back through that v, which actually means this was just not an efficient way of doing this at all. I then realized I'm better off taking out the k. I could use log laws here to say that this is log of k plus log of this thing, with a minus in front, of course, minus all of this stuff. But of course, log of k, I mean, all of this times log of k is just a constant. So what I can do is I can just eradicate this and just change the constant and say that it's this now. Sorry, that's the old line I had. And just say it's this. I'll change this constant because all of this is just a constant. So change the constant there. And now what can we do here? Well, I think I can actually think about what this constant is. This minus, actually, I moved to there. And then, of course, log laws say this, the power minus 1 I can just, log laws say this minus goes there. And then just regular math says this becomes this. Now we can think about, well, s is 0 when v is 0, I think. But if you plug this in, this actually doesn't go away. You get 1 over v squared minus 0 squared, which is 1 over v squared. So d, I think, is minus all of this log of 1 over v squared, which we could put in. Well, we could obviously move this minus there. Again, same trick, and then flip it over. and we get this, and then we could put it into there, and I think now, final step will be to do the log laws again, right? Where this log plus this log, we can just times together the inputs, which will give me this thing here, because the front of the things are the same. So there were much easier ways of doing that, but that is one way to do it, I guess, and we'll get it. Question 3 is another centre of mass question, so let's get into the first part first. We look in the formula book, we see this helpful piece of information. They actually don't give you the formula for the volume of a sphere. They do give you the surface area though, which is weird. I want to know why they give you one, not the other. Anyway, the volume for a sphere is this. These are hemispheres, so we'll just make that 2/3, I guess. So, okay, we could work out the volume of the big sphere using radius as 2a. We could work out the volume of the little sphere just using regular a. We could also work out their respective centre of masses, where r is 2r for the big ones. That's replace that with a 2r to get 6/8 a, sorry, 2a, and replace this with an a just to get 3/8a, which is a bit above it. And now we can do that same formula we saw before. We only need to do it in one dimension because we know the centre of mass is in the middle, vertically speaking. So where is it? How far down is it? Well, we could do the same formula where we just say I've used x bar here. I'm just thinking about the fact that, I mean, it's a vertical distance down. It doesn't matter. It really doesn't matter, does it? Just know that I mean x bar to be the distance from here to here. Maybe I could just set my coordinate axis to be y-axis, x-axis, and then it makes complete sense. I think I just copied and pasted the thing from before, which is why that's there. Anyway, it's useful to know that this formula works with volumes in the same way that it worked with areas earlier, and it also works with negative volumes and areas, whereby you just take away the thing. So here we've got x bar times the total volume, which is just the big one take away the little one, because the little one doesn't exist, equals, and then we've got the centre of mass of the first one times by its volume, minus, again, because it doesn't exist, this is the centre of mass times the other volume. And when you just sort this all out, you eventually end up with exactly what they wanted you to get. So we'll have our answer there. Okay, and now the next bit. Kind of an interesting question. It's only 2 marks, is the very first thing I noticed. So I know I'm not being asked to do very much. I mean, 1 mark is for the answer. So this is 1 line of working, and then I get a mark for the answer. So okay, what do we know about this picture one? Well, we just worked out O to G is the distance this. We know the distance O to P is 2a, because it's the radius of the sphere, right? Of the big sphere, or hemisphere. And now, it would make a lot of sense for me to just make this alpha. I mean, it looks like it's alpha. There's something quite weird going on here about line of vertical plane which passes through the greatest slope of the... something like that. I think that's just telling you this is alpha. That's what I hoped it was doing. And then I just did sine of alpha is this over this. You have a calculator, so the a's just cancel and you just type it in. And you get alpha is this. Turns out that's correct. And again, the reason I was fairly confident that was correct is because it's only 2 marks. So I'm not being asked to do anything greatly intelligent here. This seemed like it was probably right, and it's not a lot of work, therefore it's probably the right answer. Good. Question number 4 is a really nice question, I think, about, it's the first chapter, isn't it, on, I can't remember what the name of the chapter is, it's the first chapter. You have a few formulas in here. This string, the first thing that confused me a little bit, the string is length 2L. The string goes from here, down to there. So if you call this distance BR, this distance is 2L minus BR. So okay, the total length of the string therefore is 2L now, which is good. We can actually just do Pythagoras on this. Again, only 2 marks, which means this is not a lot of work and it's not difficult. And it turns out I didn't think this was going to work, but it totally works. You expand it out, the BR squareds cancel, and you just end up with exactly what they wanted you to get, which is good. I actually didn't think that was going to work. I thought it would just end up cancelling, but that's nice. Given errors is negligible, finds this thing. So okay, we have what else do we know here? We know that we've got a mass m here, which means there's a bunch of forces we can write in, right? We know that this length is 3L/4, we just worked that out. We've got a tension in the rope this way. I mean, we're being asked, or the string, we're being asked for that, so that's good to label. We've also got the same tensions this way, of course. We've got an acceleration of v squared over r, where r is this. That's just the standard acceleration towards the center when you're moving around a circle like this. We can simplify that, I guess, to this, because we know that r is this, so I put that in, so that's that. We also have mass mg going downwards, And so actually I can work out the tension very easily right now, as soon as I'm looking at this, because I'm thinking, well, the only up and down forces, if I call this angle here theta, this force up is t sine theta, and that must match with this mg. So t sine theta is mg. I can see very clearly that tan of theta is L over 3L over 4, which is just 4/3. And then you can picture the usual 3, 4, 5 triangle, opposite over adjacent 4/3, 3, 4, 5 triangle with opposite 4, adjacent 3, hypotenuse 5. Sine of theta is therefore 4 over 5, cos of theta is 3 over 5, just imagining that triangle. So therefore t sine of theta is just 4/5 of t, and that must be equal to mg. And so we get t as that. And then find big V. Well, again, we just sort out the forces going horizontally now. We've got a force of t cos theta this way, plus another t here. So t cos theta is from this one, going this way. Another t there, and that must equal m times the acceleration, which we know to be this. So that's what I have there. And cos theta is just 3/5, so 3/5 plus 1 is 8/5. Of course, the m can just multiply by that. That's good. We actually know what t is, so we can just shove in t here. I think I actually did some stuff first, but then we can shove in t, and we can find v squared by cancelling the m's, doing a bit of work here, square rooting everything, and we'll have our answer for v. I think that's the entire question 4, so that's good. Question number 5, that is what we need to move on to now. Another question about a string and some mass on it. So okay, we've got some fixed point O, and we're holding the string horizontally across. It says somewhere. Yeah, taut and horizontal, and it's going to be fired up at a speed of u. So of course it's going to start going in a circle, because this string is just going to carry it around in a circle like this. So that's cool. We've got, what else do we know here? Find the least value of u, so this stone will move in a complete circle. Now, the thing is, you need two things to happen for it to actually get around a whole circle. And you need to think about what's happening at the top is the key idea here. Now at the top, you've got some other speed v going across, which is probably different to u. You've got a tension coming down, you've got mg coming down, you've also got mg coming down here, of course. And you've got that acceleration we saw before, v squared over r, where r is equal to a, because that's the length of the radius of this circle that it's on. Now, for this to make complete circles, we need the tension in the string to not be 0. Right? If you imagine firing this very slowly, in real life, what happens is the ball kind of collapses towards the center because there's no tension in the string. And so as soon as there's no tension in the string, it just collapses inwards. So you need to fire this fast enough to keep tension in the string. So we need tension to be bigger than 0. But looking at this, we can just set up F equals ma here. And so we'll have t plus mg equals m times this. Now before I do that, I can also set up something else, which is to do with the energy. So the energy in this system right now, to start with, it's if we define this to be the ground, I know it goes around in circles, but if we define this to be the ground, half mu squared, which is the amount of energy in the system right now, because that's just, of course, kinetic energy with speed u, that must be equal to the gravitational energy that it gains by being a distance a upwards from where it was, plus the new kinetic energy that it has. Right, so that's what the energy equation says, that the energy to start with equals the energy to finish. But also what I was saying before, t plus mg equals m times this, r is just a. And now we need t to be bigger than 0, or equal to 0. We just need it to always be there. And so what we need is we need this, I think, this minus this, of course, to be bigger than or equal to 0. So just moving that to the other side, then just saying, if t needs to be bigger than 0, then so does that thing over there. So this needs to be bigger than 0. Cancel out the m's, of course, they don't matter. Move across the g, times by a, which is a positive number, so that's fine. And we get this, which we can then put into there, I think is what I'm doing here. Did I put that into there? GA, yeah, that makes sense, good. So I put that into there. And of course, what I can also say is, I know v squared needs to be bigger than this, or equal to. So if I replace this with something that's smaller than what it actually is, I'm going to make this entire side smaller, and so this is now the larger side. And now, of course, the m's will cancel, these will actually go together, and now we can square root, and we'll end up with that being our condition for u. Now, the string will break if the tension is equal to this, apparently. So, okay, apparently if you put too much tension in the string, it will just snap, like if you stretch an elastic band too far. So the string will break if this, given u is this now, so we apparently being told u is this, finds the angle the string is turned through when the stone does break. So we're thinking about a situation, not going straight up, but maybe thinking a bit like this, where there's an alpha angle alpha to the horizontal here, and apparently there's some time when this when the tension gets too big and it breaks. Now I know that this does not happen at this point during the journey. It happens during this point, when you've sent it all the way round and it's down here somewhere. Now there's two reasons I know that. Firstly, tension here is actually working against the mg, therefore making it do more work and be larger and therefore more likely to break. But I also know it's happening down here because the velocity is bigger down here. Because it's lost gravitational energy, the velocity is going to be bigger down here to compensate. Right, again, conservation of energy. And that means, of course, the acceleration of the center is larger, which means, again, t is going to have to be larger for that reason. Again, putting more pressure on it to break. So it's going to break down here somewhere. If you've done questions like this, you just know that that's the case. Otherwise, you just need to think it through. I've labeled this angle alpha to the horizontal here, which I regret doing now, but I didn't want to change this line. So I'm just going to put alpha here. And let's sort out this stuff over here. So I've labeled everything that I've got, and let's do some sorting out. So the first thing I'll say is that t minus mg sine alpha is ma. So this is just f equals ma, and I'm working this way. That's f equals ma in this direction. Now this mg sine alpha is a little bit annoying to get. What I said was, well, if you imagine this for the component of mg coming out this way, now I know alpha is by corresponding angles. If you did a horizontal line here and a horizontal line there, alpha is this one, which makes this 90 minus alpha, because this is a 90 degrees. So if that's 90 minus alpha, this is mg cos of 90 minus alpha, because it's next to the angle. But cos of 90 minus alpha is just sine of alpha, and so therefore it's just mg sine of alpha. So that was my logic to get there. If you had chosen a better angle, you could have done that a bit better, but that was my logic to get this. Of course, that's the first thing I need. Well, in fact, I also know that tension is this when it breaks. So I'll replace that with that, and I've got that there. And there's some sorting out you can do there, cancelling some stuff, and you get that. Now, what else do I know? Well, I also know this stuff to do with the energy, right? So, okay, what does the energy say? Well, I've got this much. To start with, I had this much kinetic energy, because we know it was fired with this speed. So half mv squared, this squared is just 4 ag. So that's my starting energy, because there's just kinetic energy in here. I'm defining this again to be kind of my base height. So I'm saying there's no gravitational energy here, potential energy here, sorry, I should say. Now, to end with, I've called this speed v going down here. So it's got half m big V squared, and now it's actually, because it's lower down, it's lost potential energy. And if you draw a little triangle here, this distance here is a sine alpha. It's opposite the alpha, so it's a sine alpha. So this is how much potential energy it's lost. And now I can sort this out, of course. All the m's will cancel, as they always do, or usually do. You could sort this out for v. I think I rearranged this for v, and my plan, because they've asked me for the angle, my plan was to put this v into here, which is what I did, and now I think I could work out the a's, the alphas. These a's will cancel, these g's will also cancel, and then 11 over 2 is 5.5, minus 4 is 3 over 2. Add that to get 3, so we end up with this, I think, from there. I think we end up with this. Divide by 3, that makes alpha equal to 30. I originally put pi over 6, but then it turns out the answer scheme said had an answer in degrees, so I just changed it to degrees. Of course, if this alpha is 30, the total angle turned through is 180 plus 30 for 210. Now find the magnitude of the acceleration the instant the stone breaks. Now we know the acceleration going into the center is this. So that's cool. I think I could work out v as well quite easily by just putting in sine of alpha as a half into this equation we had before. I think that's just an equation we had earlier, isn't it? Yeah, it's this one down here. So I'll just put that into there to get this. And so, of course, this is just v squared over a. So that's 5g, which is nice. The acceleration this way, or the component of the acceleration to the center of the circle, is just 5g. Now, what about the component acceleration tangent to it? Because you've always got the two components to the center and tangent. Well, we could just set up a little f equals ma tangent to the center to get that done. So this is just we talked about how this was mg sine alpha there. Therefore, this is mg cos alpha. This component of this mg. So force here is mg cos alpha. And that just equals m times the acceleration tangent, or is this, yeah, tangent to the circle, I guess, that's moving on, which I've just called XL in brackets because I was losing my mind at this point and couldn't be bothered to do this properly. The m's cancel. Cos alpha is cos of 30, which is root 3 over 2, and that's the acceleration in this direction. So all we have to do now is do, for the magnitude, it's just Pythagoras, isn't it? It's this squared plus this squared square rooted, and we'll end up with this here as our answer. And we've, I think, got 2 questions left, question 6 and question 7. So let's start this up. Question 6 then is on simple harmonic motion. So first we're going to find the equilibrium point. We've got a string hanging from a ceiling, essentially, we can imagine it as, with a mass on the end bringing it down, stretching the string, obviously. So let's find what that stretch is, where we've got a tension in the string, we've got an mg going down. So if this is an equilibrium, it is just kind of resting here. We have t minus mg equals ma, where a is 0, so therefore t just equals mg. Of course, tension by Hooke's law is this thing, so we'll put that in. Lambda is this, so we'll put that in. The natural length is just L, so we'll put all that in. The mg's cancel, and we have x is L over 2. So therefore, the string is already natural length L plus L over 2 gives us a distance of 3L over 2 as our points to our resting point here. Good, our distance to the resting point here. So now it's pulled down a further distance L. So there's going to be even more tension in it, and then of course it's going to move up and down in simple harmonic motion, except it's not really, because the moment it reaches the top here, the string is going to be slack. It's not a spring, so it's not actually going to come down with simple harmonic motion again. So it's going to initially move with simple harmonic motion, and then it's going to do something else afterwards, which we'll discuss in a second. But first we can say, yeah, sure, that's just simple harmonic motion to start with. So m minus t equals mx double dot, of course. That's fine. So we have this, we've got t is we've got it's still using this here. Now its extension is going to be the half L. So the half L is just the extension to the equilibrium point, and then plus any more extension as x is the displacement from your equilibrium point. So that's the half L there, and then any extra x that is currently stretched to in the middle of this simple harmonic motion. So that's that. We can therefore simplify that, and these things cancel. You should always be ending up with something like this and no constants left over, so you can just sort of fudge this until you end up with no constants left over. I'm sure we've all been there. But anyway, we end up with this. You just have to state that simple harmonic motion with omega squared equal to this bit here. So that's good. The period is always 2 pi over omega. That's just something you have to remember. So we do 2 pi over this thing, we get this, which is just simplifies up eventually to that. So that's good. We come to instantaneous rest at c. So initially we have 0 velocity, we're just being pulled down to here, but we do have a lot of tension in the string, right? So we can do an energy balance equation here to say, initially we just have lots of energy being stored in this string, and at the end, when it's moved up all the way up here, there'll be no energy stored in the string because it will be slack, and we'll have no speed velocity either, because we'll be up and at instantaneous rest, and the only thing we'll have is all of this gained potential energy. So we can just set up that the initial elastic energy that's stored in there is equal to the gained potential energy having risen a height of h until wherever it stops instantaneously. So therefore mgh, which is the increase in potential energy, is just equal to the elastic energy of this stored in the string, which FM1 tells you is this. This 3 over 2L isn't this 3 over 2L, it's the L from here plus the half L that the string was initially stretched to get to its equilibrium point. So that's all of the elastic energy lost is to get the string slack, and then of course it's just slack to get all the way up to here, so it doesn't really matter. But it's the 3 over 2L to get from the just the normal distance of L plus the 3 over 2L to get it all the way on there. So that's where that is. When you just sort this out, you get h as 9 over 4L. So in the final 5 marks, find the time it takes to get from B, which is the bottom of this, all the way up to that initial instantaneous rest point. Now, we can model it with simple harmonic motion until the string gets slack, and of course the string gets slack at a half L upwards here, because remember that equilibrium point was at half L. So when x is minus a half L, because we're going upwards, and I was taking x to be positive initially, going downwards. So when x is minus a half L, we can model simple harmonic motion with this formula, because we're starting at the end of the simple harmonic motion at the bottom here. So we can use this, we put in all the stuff that we've got, L's cancel, obviously, we rearrange that, we get t as that. So that's how long it takes to get to the point where the string would be slack.
And then when the string is slack, it's no longer following simple motion, but it is just going to be following basic laws of motion. We can just use that, right? It'll have some speed that it's going to when it's slack, and then it will just go up some other distance until we get there. So, okay, we can do some work here though, because we know that the total height it gains is this. We just worked that out. It's already gained 3 over 2L to get to its slack point. So we do this minus 3 over 2L tells us the rest of the distance it's going to go up, or displacement that it's going to go up. So we get this. So this is our further displacement it will go before it's at instantaneous rest. Of course, its final speed will be 0, its initial speed is 0, and its acceleration is minus g. So it goes, sorry, its initial speed isn't 0 because I'm taking it from the point where the string is slack. I don't know what that is. So we'll just say A is minus g because it's being pulled down. I'm taking down to be negative now at this point, which I guess doesn't really matter, does it? 3 over 2, yeah, I'm taking up to be positive. It doesn't matter. I was doing it the other way around, but it doesn't matter anymore, does it? We can use the formula, which doesn't have u in it, which is this one here. Of course, v being 0 helps. It clears out this term. And we just solve that for t as that. We can add together this t with this t, and we'll end up with our final answer. Question number 7 then. So firstly, shout out to a lot of behind-the-scenes crew of the R2 Drew 2 factory. Raj, my colleagues John and Sam, Jay Winfield and S. Wilson Maths on YouTube. I had a hard time with this problem, especially with the first part of this problem. I just didn't really understand, lots of us for a while didn't understand what element we needed to do of this to work this out. Eventually we got there. What we're going to do is we're going to consider a semicircle like this, with a radius x, and then just a little extra bit here, which we'll call dx, a little bit of x. And I'm going to aim to work out the area of this kind of, I can't even remember what this is called, this kind of arc here. It's not really an arc because there's a length here. But anyway, I'm going to work out the area of this bit here. And now, of course, to do that, I'm going to call it dA, because it's only a very small area, right? Because this is just dx. And what I'm going to say is, that's going to be, well, the whole sector here is just pi over 4, because it's a quarter of a circle, times r squared, where r is x plus dx. So the area of this little bit here is pi over 4 r squared, where r is this plus this, minus pi over 4 x squared, because I'm going to take away this bit beneath it. And that should just give me this kind of ring here. Of course, when I do this, when I expand this out, I get this. And of course, this pi over 4x squared and this pi over 4x squared cancel, and so we're left with this. But when you have an order of magnitude dx squared, you can just ignore that, because this is such a small length that when we square it, we can just say it's basically 0. So we get the dA is basically pi over 2x dx. And now what I'm going to do is I'm going to integrate that between 0 and a. Well, firstly, I'm going to say mass is density times area, sort of, where density is this thing, and that's KOP squared. But if I just take x to be some distance away from the origin, I can just say that's x squared. So I'm just going to say it's going to be k times x squared times this area here, and that's going to be my little dm. It's a little dm because this is a little dA, isn't it? So small area, small mass. But of course, what I can do here is I can just integrate this between 0 and a. So I've essentially got the mass of lots of kind of rings here, and I'm going to integrate them, increase x gradually from 0 to a, and that should give me the total mass of the entire thing. So just integrate this thing between 0 and a, integrate dm, of course you just get m. This should go quite nicely from here, I think. Obviously, some pi's cancel, which is good. Anyway, this is just regular integration stuff, of course, and we end up with the mass is lambda over 2, which is good. Now, for the second part, in terms of the distance of the center of mass from O, now what we need to do here is firstly we need this thing here, right, because we haven't used this yet. So what this thing will do, because it's talking about arcs here, is this is going to give the center of mass for each of those kind of infinite arcs that we were drawing earlier, just before. So let's do this. Well, 2a is 90, or pi over 2, of course, so that means alpha is pi over 4. So we shove this in, sine of pi over 4 and pi over 4 here. We, of course, get this. Sine of pi over 4 is root 2 over 2. If you want to write it like that, you bounce the 4 up, you cancel. You get this. So that's the distance from O, that the center of mass that each of these rings have. So what I'm next going to do is I'm going to say the center of mass of the entire thing. I'm going to do that formula where we sort of do integral of x, y over integral of y. And so here's the y bit. The integral of y is just the mass. We just did that before. And then the extra thing that I need here is to just shove
the actual center of mass for each of these individual rings into here. So essentially, we're using this integral of x, y, dy formula, x, y, dx formula, and integral of y, dx at the bottom here. Of course, this integral is just m, we've already found that, so we're going to put lambda over 2 in here. And again, once you've got all of this, this is just, pretty easy integration. All the constants obviously come out, you integrate, you cancel a lot of things, and you put in the 0 and the a, which the 0 goes away, and you just end up with your x bar being that there. So yeah, I thought a really tough question. There was a lot to get right there, but I guess it was the last question, so yeah, thanks for watching.